Hello, this is a video on the XP series, the Digitech XP series, focusing on the XP-100 here, which is the whammy-wah variant. There's also a 200, a 300, and a 400. I'm going to be talking about this unit, how it works, the circuit board inside, the processor, how I reverse engineered the code. Going to be going into detailed analysis of the code and how I got past one of the problems that has been in the excellent mod that's going around, the XP-All. The XP-All puts all of these units together, the 100, 200, 300, and 400, into one with the selectable switch on the front. That looks a bit like this. It has the switch where you can switch between each unit. Now, you can skip the background section if you're already familiar with the XP series and how the unit works. I will be going into a bit of hardware in the background and also extra hardware in the hardware section, so be aware of that. Okay. This is the XP-100. It has a user manual, so you can find this on the internet. It's quite easily available. We can see here this is the sticker for this little LED display here, and it shows you the preset number. So it goes from 01 all the way to 29. There are 29 presets, and there are 6 user programs. These are very important bits of information, and we should remember that. In fact, we will remember it with the help of an amazing program called Notepad. So, things we know. There are 6 user presets, and there are 29 default presets. So, can we get any more information about these preset numbers? Well, if we go back to my desktop here, we can see that this is the space station, and it has more presets. The preset numbers go all the way up to 40. Now, we know from the good work, the people with the XP-All mod, that when you are in a mode that has more presets, and you switch to a mode that has less presets. So if you're in the 300s, you switch to the 100s, then it defaults back to this very first preset, the volume preset here. That's important. Default preset on incorrect value 01. And I should have said before that, when you start the unit, it starts in its previous state. So it starts in its previous state. These will come in handy later when we come to reverse engineering. There's a lot of things in the manual, so it tells you how to do some things, like what the controls are. There's a few special functions, so there's a you can store user programs. I call them user presets. There's a tuner mode, and this is the factory reset and the pedal calibrate. They're combined into one feature, I guess. I should say that the pedal that is on these allows you to control whatever the preset is. So if you're in the whammy mode, for example, here, this will control the pitch shift of a note that you're playing into the unit. Let's start on hardware. There is a PDF easily available online of the schematic for this thing. So you can see some title page here. This is all the analog circuit. So the input is here. So for these input, output, there is an A to D here, and then this goes to the digital signal processor. And then there's an input here from the digital signal processor. So imagine this is processing that goes around here. And then it gets amplified to the output. It's that simple. They just use a lot of triangles to get there. Okay. This is the processor. It is an 83C154. Then there is a program memory, which is this chip. On the XP-100, they did a re-release where they removed this chip. They actually integrated the program into the main processor. Bit annoying. Not really a problem though. You can still boot from external memory. You just need to change a single component, which is this resistor here. You see where it says omit. It means it's not there. You also see omit on this memory part, because with the masked, they call it a mask ROM, the program memory that is stored in here from factory. When you have it in there, you don't need this chip to store the program memory for you, of course. But in all the 200, the 300, and the 400, this chip exists. Then you've got another read-only memory. They're called read-only memory. They're not read-only. This is an EEPROM, E-squared PROM, rather. It stores the little settings that we need between each thing. So unit starts in its previous state. That's all stored in here. As we saw from the manual, there's a calibration for this thing. So the calibration is also stored in there. And we can see that via these lines, it communicates with the processor. There's not much else important on this page. We might get into the LED display, which is this thing. There's a bunch of lines out, which connect into here, which then connect into here. Next page has the digital signal processor. Can't really get much from this page. It's not very important. This chip is a bit of a family secret for these guys. They don't like talking about it. No data sheets for that thing. And then just a list of parts. Mainly we'll be focusing on this page because we need to read off the port numbers here and see how this shifts. And this is also doing some shifting with the data line here. Okay. The processor is this, and this is its data sheet. This is one data sheet. There are many of these processors, all made by different people. This is Oki Semiconductor. There's just some little specs here. The main thing to gather from this document is that it's an 8051 processor. 8051 is made by Intel. It's not actually called 8051, but that's just a very standard name for it. And when we do the reverse engineering, that's going to focus on 8051 assembly. Not particularly hard stuff. It's quite similar to x86. It also borrows some features from what you might expect in a RISC architecture, which doesn't have many instructions. There is a few pages we'll be concentrating on here. This one's very useful. It maps some pins. So you can see we got RxD here. RxD is just written as RxD here, but in the code it's called P30, which is P3.0. We'll get into that with the code. And then there's another useful page later on. This is memory maps. The entire memory goes from 0, which is down here, all the way up to FF, which is here. But the actual RAM area is down here. There are banks of registers here. We can go between these banks with instructions. There is something called bit RAM, which is RAM that is bit addressable. And then there is just standard RAM. This you can see this goes from 7F to 30. That's the largest area of RAM. And these are special registers. You can see there, special function registers. This is quite an important one. It tells you where all the interrupts are. So you can see CPU reset start at 0. This is address 0. External interrupt 0 happens at address 3. That means that when there is an external interrupt 0, the processor will stop doing whatever it's doing and start executing at address 3. Same goes with this timer. It will start executing at address B. This will start executing at address 13, and so on. So this is going to be important. But the biggie is kind of this CPU reset at 0. Not all processors will reset to address 0. Okay, that is basically everything on hardware. Actually, two more small notes. The expression pedal, so that's this thing, is read in here. It's a opto transistor, which basically means it senses light, and that goes into the right channel, A in R, audio in right, from this 8D converter, which is analog to digital. That goes to the TMS, which is the digital signal processor. So this leads us to some strange conclusions. Instead of the pedal position being read by the processor, it's actually read by the digital signal processor, which is what does all the audio stuff. Very strange. From my analysis, I have found that this digital signal processor does report back the pedal position to the main processor. Bit of a strange way to do it. The other note is that we can tell from that, we could tell without looking at the code that this DSP reports back the position to the processor because of the manual. We can see in here, let's find the noise calibration. To calibrate the noise gate threshold, press the button. Yep. The display will show the threshold range from 0 to 99. That's the important bit. That means when you rock the pedal forward, the DSP communicates with the processor, tells it the pedal position, and then the processor decodes that and displays a number. How do we know that the processor is responsible for displaying the number? Well, we can look at the schematic and see that the processor has a direct connection to the LED display that doesn't go anywhere near the digital signal processor. The inside of the XP-100 looks like this. This is the DSP. This is the main processor. So you can see that Digitech have written their own name on it, taking all the credit. And we can see a lot of empty spaces. So this is empty. This is empty. These three are empty. I think that's connected on the other side, so it's not actually empty there. There are a lot of things omitted in the XP-100 because it is, in hardware terms, software terms, the most basic one of the series. That's one of the reasons I'm looking at it. I looked at it first. The other reason was I'm more interested by this one than the others. So this is actually the position for the EEPROM, the program memory, that is not present in some versions of the XP-100, the later versions. So this particular one has the program integrated into this processor. This missing chip here, we can see that all it's doing is taking wires from here and putting wires to this device. We can see it on the schematic. It's this. You can also see omit. All it does is take in a bunch of address lines and output a bunch of address lines. In these missing spaces are RAM for the DSP. So if we look back at the schematic, you can see we've got 4 of these, and this one does not have an omit, but then we've got omit, omit, and omit for these 3. The XP-100 only has 1 of these chips installed. The XP-300, which is the space station, requires a lot more memory and has all 4 of those positions occupied. Alright, this is the main part of the video, the bit you've been waiting for, the bit I've been waiting for. This is the reverse engineering. We're going to use IDA, which is the interactive disassembler. Right, let's disassemble new file. This is the binary for the XP-100. You can find it online in places. There are a few links to it in this converting document. I have an old version here. These are the good people who worked on this, published it all. Right at the bottom gives you a few links, XP schematics, and binaries. So that's where I got this one from. You can see it's only 32 kilobytes. In fact, most of that 32 is blank. So I mentioned before, we've already looked at the processor and we know that it's 8051. So let's look through here. Intel 8051. Select that. Now I'm going to disable the analysis. I'll tell you why. The analysis will look through all the entry points and try and do all the work for you. The reason why we don't want that is because it's going to look at all of these entry points, and possibly more. There are many varieties of the 8051 processor. And it's going to start disassembling at those locations. We can't know for sure that all of these interrupt vectors are actually used. And if they're not used, then anything could be there. It could be data, it could be half an instruction, or just garbage, just nothing. So we can't rely on IDA's auto-analysis to help us for this, which is unfortunate. Perhaps there's a way to force it to only disassemble from the reset vector, which is the one we know, the 0 location. For now, we're going to assume that's the only one we know. We're going to start at the reset vector and work our way from there. Alright, we set the processor analysis disabled, and let's go. Alright, we're going to choose this processor. I've been through most of these and figured out this one is the most accurate. It has the right amount of RAM for the processor that we're working with. Yeah. Okay. So, we know that when the CPU resets, when it turns on, it's going to start executing at vector 0. 0 is right here. Let's convert that to code. First thing we see is LJMP, which is a long jump. It just moves execution. So it starts executing at IE0, which is right there. While we're at it, let's make this a subroutine by pressing P. Oh, before I forget, let's set up our segments. So we're going to segments here. We'll see that it's only treating up to 800 as actually code. We can't be sure of that. It could be the case that the whole of this binary is code. So let's delete this ROM segment and and edit the code segment to 7FFF. can't quite take it to 8,000. Not sure why. Confirm that. And there we go. So this jumps to IE0, and we can say that that is also a subroutine. But then IDA says the function has undefined instructions at 09. Well, we know how to fix that. Press C, convert to code, and now it's a subroutine. I don't know why IDA does this. It hasn't quite got the end of this subroutine right. The end is actually 12. Alright, now we can go into graph view. What we're looking for here, the goal is to modify the code. And what we're going to be modifying is the combined unit. So when we've got our XP all, and it's got these 4 settings, and we're going to be modifying it to not share the same locations in EEPROM for these 6 user presets. We know that these user presets are preserved between power runs, so they must be being stored in that tiny little chip that I showed you on the schematic. That is right here. The issue with the XP all mod is that, and the Jetpack mod, which is a similar thing. When you set up your presets, your favorite presets for your XP-100, and you flick over to another one, they're going to point to different locations. It's not going to be right. And then if I go to my beautiful space station and set up one of my presets to be number 39, one of my user presets, and then I switch this back to 100 and try and load the preset, it'll be all wrong. It doesn't know where 39 is, because this one only goes up to 29. That's the problem we're going to be fixing. I am going to go through the modification for that to fix it, and how I know that I can fix it. So there's a pointer which I got in the reverse engineering, and I thought, can I do this? Is it possible? Turns out it is. It's very easy, in fact. What we're going to do for this reverse engineering, to get to our goal, to find out what to modify, is to look at what we know and look at what we want to know. So we know that it starts in its previous state, and we know that it preserves these user presets. So on initialization, on boot, it's going to load from this EEPROM the 6 user presets and its previous state. We'll also see some checks for incorrect states and a reset so that they're put in a correct state. And that's what we can gather from what we already know without even looking at the code. Let's go to IDA. So this is, you can see a small loop here. That's what this green line means. What it's doing is, into R0, it's putting this number, which is 127. Lines up quite nicely with a number we've seen before. If we go into our processor sheet, you can see that 7F is the top of user data RAM. Keep the number in mind. There's your 7F. It clears A, so A is now 0, and it moves A into the address pointed out by R0. So on the first loop, it's going to move 0 into the address 7F. Now, what does that mean? Well, we'll see. Need to look at the bigger picture, because then this loops. This is DJNZ, which means decrement and jump if not 0. So it's going to decrement R0. It's going to make it 1 smaller. and then it's going to jump back if that is not 0. This is going to carry on until R0 is 0, and then it's going to go here. A is not going to change throughout this process. A is the accumulator. It's always going to be 0. So it moves 0 into every RAM address. This bit of code just clears the RAM. That's all it does. And then this adjusts the stack pointer. Not sure about this line. And then jumps to 1E. Alright. We can see here the processor does a mov, does another mov, and then IDA doesn't know. It thinks it's as a byte. We know it must be code, because what's the processor going to do after this instruction? Well, it's going to move on to the next instruction, which is this. Convert that to code, we see some calls, mov, mov, call, and then what's it going to do after this call? Well, it's going to execute the next instruction, which is right there. And there's some more calls. Alright, now we know this is a function. You can press P, convert it to a function. Again, IDA has got the end of the function wrong. It's actually something more like EB8-1, which is the next byte along. Alright, this should give us a much better view. Alright, so this is the main program, the main loop. You can tell it's a loop because of these thick blue lines. IDA recognizes loops and makes their lines thicker. So you can see all these are not so thick, whereas this one is thick because it's part of the loop. And they're all going to this one part here. That's the highest up this massive main loop goes to. What does this tell us? It tells us that everything above this was not actually part of the main loop. It only happens once now. What only happens once? Well, we only boot once. We power it on, this gets executed, it initializes the device, gets everything ready for the main loop. So we know that all the code from here to here is initialization. Alright, it's a good place to start. The very first thing it does is execute this little function here. I press P, I know it's a function. I can tell you because I've already looked at the code, this doesn't do much. It's actually a wait. I called it busy wait. You can take the time to look at this, see what it does. It takes a number, R6, R7, and just counts down through the number again and again and again. You can see this conditional loop here. You can see it decrements R6 and just eats the processor time. So it's a wait. It serves for timing purposes only. This doesn't set up anything, doesn't write to memory, only uses these 3 registers here. The next function is bytes. Let's convert it. Pressing P, and now we've got ourselves a subroutine. This looks right. Immediately this looks right. It's doing support stuff, setting up the timer, setting up the control, setting up more timer control, setting up interrupts, more setup on port 1, and another interrupt thing here. You can figure out what all this does by looking at this document here. So I believe the one we need is tmod is the one we're looking for. Tmod. You can take a minute or so and look at this binary and see how it corresponds to these individual bits of the tmod. But basically what it does is it enables timer 1 and That's all, really. We can see that there's timer 1 high and low here. So that's F9 and D6. We can open our calculator, type in F9, D6. That's a big number. So what this timer does is, whoops, timer counts up to that number and then executes code at timer 1 vector, which is, if we go back to our processor datasheet, timer interrupt 1 start is at 1B. That'll give us some pointers for later on. Not necessarily too useful to our goal for here, but good information for carrying on with the reverse engineering of the XP-100. Alright, let's not lose sight of our goal. We want to figure out how these presets are loaded in at the beginning. We're going to use this important information here. When the preset is out of bounds, it gets reset. So, we know there's only 29 of these, so perhaps there's a check for the number 29. What's 29 in hex? It's 1D. So let's go back to IDA and just search for 0x1D. First result. It's a subtraction of A. So this does A equals A minus 1D. And then there's a jump if carry. Jump if carry means jump if the carry flag is set. Now the carry flag is set is if A is less than 0x1D. A is loaded from RAM 36, so let's just put that in there. That means that this code is executed when RAM 36 is greater than or equal to 0x1D. 0x1D is the biggest number we can have in our presets. What we see here is that it clears A, and then it puts A0 into RAM 36. This looks like it's taking us back to a known value. It's going to be in range. There's also one more thing we can work out here. So the default preset is 1, but the default here is 0. What we found out is that this RAM 36 is actually the preset number minus 1. So while preset 29 is a valid state, RAM 36 being 29 is an invalid state, because that is almost like saying preset 30, and we don't have preset 30. Alright, so we found that this resets the value. Now, this value must have been loaded in from somewhere. It's going to be loaded in from the EEPROM. Let's look for cross-references. Do that by pressing X. Actually, to make that easier, let's rename this function. Call it init. Now this initializes the pedal. Let's look for cross-references that are inside init. So here we go. This is the first one in init. It's a write. Let's go to it. Okay, it was right in front of us, in fact. It's getting its value from A, and A is getting its value from R7. So let's say that RAM 36 equals R7. That's what this line does. And just before that, you may be thinking, where does R7 get its values from? Well, it's getting its value from this function here. Let's look at this, convert it to a function, and look at it in graph view. what do we see? Where IDA has seen for us, seeing some ports, port 1, port 1, port 1. It's modifying this P12 twice. At the beginning, it sets it. Set B means set bit. Set bit 1.2, that's what 12 means here, to be high. And this clear sets it to be 0. Now, P12 is actually a wire on the processor. It's an output. So let's look at the datasheet. No, let's look at the schematic. And we see that 1.2 is here, and we trace the line, and it goes into this pin, which is chip select. That's what CS means. A lot of chips have this, so if we look at that DSP, it will also have a chip select here. So that basically enables the EEPROM to work. It's saying, I want to read, or I want to write, I want to use you. So this enables the EEPROM right at the beginning and disables it right at the end of the function. I notice this is the end of the function, not just because IDA tells me, but there is a return right there. So it's a fair assumption to make that this is reading a value from our EEPROM, and we can label it as such, read from EEPROM. This has been called twice in close proximity here, and we can see that before each call there is a line that sets R7 to be a pre-programmed value. This one's 15 and this one's 14. We can see in the lines afterwards that this 14 gets put into this 36, and this 15 gets put into this 37. I guess that's just a nice coincidence. They felt like lining them up like that. Now I convert these to decimal. This is decimal 20, this is decimal 21. It's a fair assumption to make now that this is an address. The address 20 gets passed into this. This reads from the EEPROM, and out of it comes R7, which is the data that was stored in the EEPROM at address 20. So that's what this is doing. And this one is just doing the same for the other location, which is 21. So we found our read from. Now we want to find our write to EEPROM. It's going to be a separate function. How are we going to find this? The easiest way I can think of is looking for this line again. The save to EEPROM is going to be very similar to this. I will guess that it will use R7 as a register for the address. If it wasn't R7, I would just try something else like R6. Once you look at the code long enough, you realize that R6 and R7 just tend to be used very regularly as arguments to functions. So let's copy this line, go to the beginning of our program, and search for that text. It's being loaded into R6. We see RAM36. We've seen this before. We see some other things, and then this call. This looks quite promising. So let's make this a function and inspect it. This looks very promising. We're seeing port 1, more port 1, more port 1. And the same thing again, this chip select, this P12 is being enabled at the beginning and disabled at the end. This is clearly a save to EEPROM. Alright, so we've found both our read and save to EEPROM. This is where we found our read, and the save to EEPROM that we just found is in the main loop. somewhere near the top. That's not important, but it's nice to get a general feel of where it is in the loop. This is one of the very first things it does. Conditionally, anyway. You can see this red line here, that's a condition. Okay. Let's look at our goal again. So, this is things we know. So, our goal is to attempt to move the location of these saved user presets so that the XP-100, 200, and 300 do not overwrite or interfere with each other's presets. What can we conclude from that? The conclusion is that all XPs use the same memory region for saving the user presets. That's all 6 of them. This is not necessarily useful for our disassembly here, our reverse engineering, but it is useful for knowing what to do to achieve our goal, which is to make them not use the same memory region. If we make them not use the same memory region, they won't overlap and they won't interfere. Alright. So let's figure out where those presets are being read from. We know that if we have user presets that are not in the range, then they will get reset to some default range. We also know that they're being loaded on boot. Actually, I guess we don't know that, but it's kind of logical. You wouldn't really load them on the fly. In fact, if we look at the code, we can see that read from EEPROM is only executed in the init function. It isn't executed at all in our main loop. That's how we know that. Alright, so let's look at the other read from EEPROMs. This is reading address 16. Address 22 in decimal, 16 in hex. The output is into R7. It moves into the accumulator. It rotates it right. And then it takes the carry flag and puts it into this address. This doesn't really look like what we're looking for. We are looking for 6 user presets being loaded with a read from EEPROM. So let's keep searching. What about this one? Alright, we can see with this thick line here that we are in a loop. This is the loop. And it goes from here and runs around here. Generally, you can spot how many times a loop will run just by looking at this condition here. So this condition decides on the red line to continue the loop and on the green line to exit the loop. We can see the number 6 here, which is quite promising. You can reverse engineer this yourself. I don't really recommend it. It's kind of nasty with their subs and the carry flag. They didn't need to implement it like this, but I guess they programmed it in the C programming language and it just spat it out like this. They only needed to use 1 RAM location. It wasn't necessary to use these 2. So this is checking against these 2 RAM locations, which is 5A and 5.9. We can see up here that both of those are being set to 0. A is being copied into them, and this clears A. Now, let's look at what happens to these later on. This is being incremented here, conditionally, and this is being incremented here, unconditionally. So, can see that all execution for this loop will run through this block here. Now, when you're in a loop and something's being incremented every single time you go through the loop, what do you call that? It's a loop counter. 5a is a loop counter. What do we see here? 5a is being passed into R7, and then we call read from EEPROM. We know from before, we guessed from before, that R7 is the address which is being passed into read from EEPROM. It also happened that R7 is the address that should pass into save to EEPROM. I said that R7 used a LAN. And we can assume this loop is loading our 6 presets, judging by the 6 here. What values does this take? It starts off as 0. We go through our loop the first time, and it carries on, and it loops 6 times. So we know that this is going to load from addresses 0 to 5, because there are 6 numbers from 0 to 5. What have we learned? Well, now we know that our 6 user presets are being stored in EEPROM addresses 0 to 5. Write that down for us. Alright, that's going to be important. We have basically figured out most of what we need to know to do our modification and achieve our goal, which is to move the memory addresses in the EEPROM for the saved presets so that they do not overlap between models. However, let's do a bit more reverse engineering first. I know that's not been enough. We touched on an instruction before. I showed you this one. I just called it rotate right. Here's a little demonstration of a rotate left. So if we go back to our code, we are rotating A. It's usually A that gets rotated. Imagine this number here, 011, 01, 011, is our A register. What happens in a rotate left is that the value of A gets shifted like this. The carry flag gets put into the least significant bit, and then the most significant bit, which was shifted out, gets put into the carry. The opposite happens for a rotate right carry. Our carry flag will actually be over here. When the rotation right happens, our carry flag will get put into the most significant bit, and then the least significant bit becomes the carry flag, and that's a rotate right. This is a rotate right, so we know that our carry flag will be the LSB of this. So that means that RAM underscore 20.2 is equal to the least significant bit of A. Where does A get its value from? Well, we can see on this line here, it gets its value from R7. Where does R7 get its value from? It gets it from read from EEPROM, which reads address 16. And that's what that line does. Okay, so let's jump on to something else. I'm going to talk about the LED display. Alright, let's have a little recap on how the LED display is connected to the processor. So it's connected to all these lines to the LED display. These inputs called A, B, C, D, E, F, G, and dB. The only one that's really understandable here is dP for decimal place. Dig 1 and Dig 2 will be enabling for either one digit or another. And that's all we can really gather from here. I don't know what these A to Gs do without actually probing the hardware, perhaps taking the display out and passing current through it and seeing how they connect up. But there's a better way. These modules are going to be off the shelf. They're going to be in vast quantities and just popular. So if we want to figure out how this is controlled by the software and how these letters line up with digits on the display, we can just look up a generic display. So here I've done a search on DigiKey. I've looked for display modules, LED, character, numeric. I've set their display type, which is 7-segment, hexadecimal, and number of characters to be 2, just like the display on the XP series. And I clicked on the very first result. Got this. Let's look at this datasheet. Alright, it's in a wonky rotation, so let's just move that around. Alright, now be warned guys, this is an uncontrolled document, so yeah, be careful. Okay, so we see a bit of circuit here and a bit of diagram here. This is kind of what I wanted to know. A, B, C, D, E, F, G. So, kind of makes sense. This is how those lines will line up with actual characters on the display. dP was obvious, of course, it's the decimal point. This schematic tells us that these LEDs are common anode, which means that this positive terminal is common to all of the LEDs. And then you switch the negative. So to turn these off, you actually pull all of these lines high. And when they're all high, that means that all the characters are turned off. Yeah. Or you could pull this low, and then you'd never be able to set anything on these to actually turn the LEDs on. So this can be used as an enable pin for this digit, this enable pin for this digit, and then you can individually control these to turn on and off these segments. Okay, so that's the hardware side. Now, what about the software? So we can see that this is being connected in to port 0. Let's go back to WIDA, and let's do a little search for this text here, port 0. Nothing. We get no accesses to port 0. I'll tell you why. It's because this is not being addressed as port 0. We can see here that all these lines come over here into this chip. And another line, which is the clock, comes from write, or WR. This is the write strobe. So what this tells us is that this chip is clocked, meaning that its inputs get sent to its output when the processor wants to do writing. That's important. So when this wants to write, that's when the state of this bus gets sent to the output here. How can we tie this into our current knowledge of the code? What we saw on init is that there is a timer that does its thing. many times a second. We can say that it's many times a second because this is quite a small number compared to the clock frequency of the chip, which is 12 megahertz. So this timer happens again and again and again, and when the timer interrupts the processor, it goes to this address, TF1. Let's subroutine that. And it jumps to this address here, TF1_0. Let's subroutine that. Alright, this is our timer 1 function. This executes many times per second. We can kind of assume here that this will be doing displaying to the display. There's several features of the Digitech XP series that can kind of tell us that this is going to be happening anyway. There's various different ways in which it can display to the display. So there are little animations that can happen. It can also flash the digits. And we wouldn't really expect that functionality in a modular system to be put in this main loop, especially since the frequency of this main loop is not a constant, whereas the frequency of this code being executed is a constant. We'd expect things that are to do with timing to be controlled by the timer. So let's just look through here and see what we can see. There's a bunch of conditions here which will execute along different lines to achieve different things, and it all runs into this one spot here. So we can kind of group this together. We can say that from here onwards is one group, and that group ends here, and then it starts doing something here, and then maybe stops doing that something here, and it starts doing another thing here. We can see another one of these conditional branching off to another group of things here. This is how you can kind of analyze this function in a really broad way without looking at the code. We can see that most of the code on my screen right now will be for kind of a single task. So let's look at what this does. It's moving things around conditionally. We don't really want something that's conditional, because we're always going to see the display unless it's doing the blinking mode. Some incrementation, decrementation. Don't know if that's a word. Decrementing. I don't know. Make something up. Some jumping here. It could be this, because it could be that this is a flag that says, I want a blinking display. And this may be a flag that says, I don't want a blinking display. And it does some things. We can tell this isn't what we want, because nowhere in these blocks of code does it ever try to write to external memory. We know that the LED module is being talked to through the use of attempting to write. And this is on the data line. So when we say we want to write, we'll pass in some dummy address, and we'll say we want to write this data. And that's how we will control the display. You can see that without looking at the code, just because of this write here, and the fact that this is connected through to the data bus. So this isn't it. Let's look further down. What's it doing? So there's a MOVX here. This will be doing something with external memory. You can see that A is being written to the data pointer, the address pointed at by the data pointer. The thing here is that A is 0 and the data pointer is 0. this will always push out nothing, which is kind of lame. That's not going to do any displaying. It's going to do exactly the opposite of displaying. So it's not this. It does a conditional jump. It's not that. Could be this. So there's some port 1 stuff going on here. There's a port 3 thing going on here. That's a bit suspicious. I wouldn't have really thought it's this. Let's look at where P37 is anyway. So let's go back to our processor sheet and look up what P37 is. P37 is RD. If we look on here for RD, RD goes over here and is indirectly connected to the display. This isn't actually something to do with the display, it's to do with these 2 buttons here, switch 2 and switch 1. Right, let's carry on then. So we know it's nothing to do with switches, it's not this. There's some conditional jumps here, nothing interesting going on. Conditional jumps here. And then we see this MOVX here. Let's look at this one first. So this would turn off all segments, not do anything particularly interesting, just like the code up here. So here's another MOVX. It moves A into data pointer. We would expect data pointer to be 0 because that's the address. We're not using the address. A is the more important thing. A gets its value from the address pointed at by R0. Now this is actually going to address into RAM. It's not going to address into anything else. This is a RAM address. So what RAM address are we going to read from to get A? Well, we're going to read from A. They reuse it quite a lot. Now, where does A get its value from? Or should I say, where does the RAM address get its value from? It gets it from this line here, which is 2F, and then it adds on R7. So, where does R7 get its value from? Well, we're going to have to do a bit of scrolling for that. It gets its value from this A here. This A gets value from this here, which is a rotate left carry. Now we already know what rotate left carry does. It puts the LSB equal to C. I can say that it's all that it does for this line. That's because A is 0 already. A is nothing. And then we rotate in the C bit, just a single bit. That means that R7 will equal 0 or 1. It will equal 0 or 1 because the C flag can only be 0 or 1. And at the moment, our accumulator only has the C flag in it. So it must be 0 or 1. Well, let's go back here and make note of that. And now we can make note of our address. And say that the RAM address is equal to our previous value of A, which is 2F, plus 0 or 1. So this value in this RAM address gets put into A, and then we try to write that data. I'm going to use bracket notation here to signify this as an address. I should also write that this is a RAM address. Now we can see these RAM accesses everywhere. These RAM 41, RAM 41, all these are RAM 41. And then you've got your other ones for RAM 42. This is RAM 21. Well, we can also have RAM 2F. I'll just write that down, because that is one of the possible values that is going to go into this, going to attempt to be written out. This is going to write to the display. Add 1 to that, and you get RAM 30. Let's look at where this is accessed. We can see a lot of accesses. And, funnily enough, all of them are writes. You can see this column is entirely W. This stumped me at first. When I first came across this value, I saw that they were all writes to the display. Well, I didn't know it was the display at that point. I saw they were all writes to this single location, no reads, and I thought, what's the point? But that's a trap. Because you can load from RAM in this way, you don't have to use its little label here. You can load it more dynamically using this register. That's why IDA, the analysis tool, didn't spot that as a cross-reference to put in this list. So let's just look at one of these. I don't know what this is. But this is going to be outputting a stream of bits. We can see that this RAM2F is followed by RAM30, which is the other one that we said will be written to the display. Here's a 2F, a 30. So this is a 30 on its own. This is a 30 on its own. We might expect that somewhere above we would see 20s on their own. 2F on its own. Yeah, there's a 2F on its own. This RAM2F is next to a RAM30. You can see these everywhere. 2F, 30, 2F. They usually come in pairs. So if I just choose a random one of these, look, RAM2F, RAM30. These are also coming in pairs. So let's work out how this actually displays a character. Let's go back to our example, which we turned into bits. You can see that the most significant bit is a 1. Let's go back to our schematic. Most significant bit will be D7. I'll go to here to D7, and this will go to Q7, which is here, which will go to CH1. CH1 goes into A. So the bit that is in the most significant bit of our data that we're writing will be the on and off for this segment of the display. This segment we saw as the if we imagine our display to look like this, that segment is right there. That's the A segment. We've got B, C, D, E, F, and G. Alright, so that's a good start. Now, it would take a while to kind of map these out, and even then, when you look at your code and you see 1110011, does that make you think of a digit? Nah, I can't imagine that either. I made a little tool which allows me to just type in these numbers and it will show me what the display looks like. Let's convert them back into hex and type in 73.5e. What do we see? PED, meaning pedal, I guess. We can see another 2 writes down here. This is 3977. CA. What can I assume this is for? Well, if we go back to our manual, yeah, here we go. So factory reset, pedal calibrate. The display will now show PD and CA. What do you know? We just worked out that this bit of code shows PD and then CA. This is another way which you could figure out the purpose of this function here, just by looking at how the LED display works. You can tell that this is doing a wait, because we're passing in some big numbers. There's a couple of them being called in succession. First we showed this character, and then we showed this character. And of course, all the time, while these are wasting processor time, this interrupt is happening again and again. And every time it's doing this code, which will update the display. Okay, now this is the mod part of the video. This is where I'm going to walk through the steps to finding a solution to our goal and how to implement it. So, I have drawn out a little memory map for the EEPROM that stores our presets. These are the 6 that are stored so far in memory addresses 0 to 5. Let's, before looking for other places to potentially store presets, let's see what other places in EEPROM memory are actually used. And we can gather that from either looking at save to or read from EEPROM, and just looking at the cross references. So we've already got address 20 and 21. Let's just fill those with used 2021. Where's this one? This one is at 22. It's also used. Let's look here. This is our 0 to 5. This is our loop that we saw before. This one is at 29. This one is at 35, and this one is at 37. So let's just fill in those, and we are not allowed to use any of those. We can use these blank spaces in between, but not actually one of these. Okay, so that gives us a lot of space to play with. If I just copy this 6, then we can fit 2 there, and we can fit another there. That's a lot. We could even have many more. We know from the data sheet for the EEPROM chip, which I didn't show you before. The chip is a 1 kilobit chip. It has 64 addresses that are 16 bits wide each. That's the line over there. We can also see from this data sheet how this is addressed, read to, saved to, all sorts, which is covered later on. This is the instruction set, and you got opcodes and all sorts. I initially looked at this when I was reverse engineering the read from. Once I'd seen read from, it was kind of obvious what save to would look like. So I didn't need to reverse engineer the save to properly. Alright, so what we want to do is modify our binary to, instead of reading and writing from these addresses, it will use a different 6, say the ones here. This means that our new ones here will not collide with the ones that I used by the other XP models. And our modified XP code will actually look here instead. Now, on first thought, you could think about modifying this loop. So instead of starting at address 0 here, we modify this number and we actually give it a default value here, say starting at 6 and running until 11. This is not the way I did it, and there's a good reason for that. It wouldn't necessarily make the save to EEPROM solution easy. Modifying this loop here would be a hack to make read from EEPROM work. Actually, no, it wouldn't be a hack. It's actually a kind of prettier solution than what I settled with, but not as nice to actually write, because it wouldn't fix our save to EEPROM problem. You would have to do something special for save to EEPROM. And there's actually a lot more of these. I mean, look at all this. We'll find a loop somewhere. Alright, here we can see this is the saving for our user presets. I know that because it's this 39 address that we've seen before. It's doing some reading from RAM, and then it's loading that into the address. That's how I can tell that this is the saving for user presets. So I could also go about modifying this. I need to fit some extra instructions in here, probably by using a call, setting up some extra code just to add a number, and then I'll shift this along. The reason I don't like this solution is it is separate to this save to EEPROM function. It is separate to the solution for the read from EEPROM function, and we are not necessarily sure this is the only place that these are saved. If they were saved somewhere else, then we'd have to do double the work. So a better solution is to actually implement it in here. So thankfully for us, both of these accept R7 as an argument for the address, and right at the beginning of the function, both of them copy it into 5B. This is useful because we can then put some code here to call a function which we make, and it will always execute the same thing. It'll execute this line, which is common to this and this. Very simple. So I say there's going to be another function. Let's get in a little notepad so we can start writing down what we want to have in our function. Firstly, we want this line. This will be at the end of our function. So I'll write this in pseudocode first. If we want to move the addresses that would be normally mapped 0 to 5 to be mapped from 6 to 11, we just need to add 6. However, we need to be careful. We don't want to always add 6. Because, say if we want to read this value, we add 6 to that, there's nothing there. That's not going to work. We need to say, if the address is between 0 and 5, then shift it. Let's write that out in pseudocode. If address is greater than 0 and address is less than 6, then address plus equals 6. That's all that's going to happen. It's that easy. And then we can substitute this R7, which we know is our address, into our pseudocode. It's going to look something like that. We don't need to check if it's greater than 0. All numbers are greater than 0. This processor doesn't really think in negatives. So we can delete that condition. Makes it much easier. Now, to copy this to assembly, we need to think about how we would implement this condition. So I've shown you before the loop here that loops 6 times. And when the loop counter is equal to 6, it stops looping. Now, we kind of want the same thing here. If our address is not within this range, we want to not do anything. We want to carry on. We want to jump. So we can just copy the same structure from here. We'll load in our address into the A register. The reason I do that is because A is a special register, which is the accumulator, allows us to do arithmetic. And now I can subtract. So we'll subtract A. Now, let's just write out what this does. This will do A equals A minus the carry flag minus 6. This is a little feature of the sub. There's no other command for subtraction that doesn't do that. Kind of annoying. So to make sure that this C flag doesn't ruin our day, we'll just clear it. Clear C. And then we know that we're always subtracting 6. And now we want to do a jump. So we've already taken away 6, and now we kind of want to jump if R7 is less than 6. We can develop this line. Take away 6 from both sides. So this R7 minus 6 is actually our A. Jump if A is less than 0. Now, this actually happens automatically. If A is less than 0, after this subtraction occurs, I'll just get rid of the comment, then it sets something called the carry flag. So we want to say jump if carry. We're not quite done. So this will be jump if carry to modify R7. This isn't necessarily the easiest way to put this in code. You'll see this loop here has this red line, and then we actually jump out. The red line is a non-jump, and the green line is a jump. So I'm just going to say jump if not carry. This will make our loop look nicer, and we won't have to repeat ourselves in assembly or do any other jumps. This minimizes code, basically. So let's expand this. Now we will modify R7. So we already know what A is. A is R7 minus 6. So let's add 6 to A. And then we want to add another 6. So add 12. We can't just write 12. That'll actually be C in hex. We'll add C to A. That will shift it. Shift the beginning of the user preset location to be over here. I add C and not just 6 because we've already taken away 6. By doing this in one instruction, it saves us a load. So I'm going to add that to A, and then I'm going to save this back to R7. R7 is going to continue being our address. So mov into R7, I will place A. Let's specify a location to jump to. Jump if not carry to exit. And then we put an exit label here. Let's give us some indentation so we know what's going on. Get rid of that a bit more. Okay. So under here, all we're going to do is leave the thing that we're currently in, clean up after ourselves. When we replace the code up here with our call, one of these, lcall, it's going to use up some bytes. So if I click on this call, go to hex view, you can see it takes up 3 bytes. If I look at the front of here, then this first instruction takes 2 bytes, and the next instruction takes 1 byte. So these 2 instructions will be overwritten, and we still have to implement those. So let's just copy those in like that. And that's all. This code will now work with read from EEPROM. Oh, but of course we need to return from our subroutine. And this command will mean that we continue executing this read from EEPROM function. So let's see how the implementation would work for save to EEPROM. We know that our call takes up 3 bytes. That'll take up these first 2 bytes of save to EEPROM. But then the problem lies in that we don't have a nice boundary here. Our next opcode actually spans across these 2. So if we were to put a call in these 3 bytes, then the processor would try and execute 5C. Could be anything, I don't know. It's half of an instruction. We don't really want to execute half of an instruction. So we will overwrite these 2 and corrupt this instruction. To get around this, I will write the call here and then put a NOP here. A NOP is quite simple. It stands for no op, which means no operation. Does nothing. And in AT51 assembly, it's just 0. Okay, but now we're removing this instruction completely. We still need to execute that. It might be important to save to EEPROM. So let's see how that's going to play in. It moves R4 into this RAM address. We could do that anywhere. That could be the first thing we do, if you like. So that would have fixed our problem with save to EEPROM. Now let's check that that would still work in read from EEPROM. We're moving R4 into 5C. You can see here that it does use, it does use 5C, but it puts A into 5C. Now, you may think, oh, that means we can't do this, it would cause a problem. But it doesn't, because we're just loading in 0 here. This code, which will stay in read from EEPROM, will just say it to 0. It doesn't matter what value we put in here from this line, because it's just going to get reset over here. However, in save to EEPROM, it will save our ass, because this instruction won't exist anymore, and we still need to do the same job. Otherwise, save to EEPROM won't work. And that means we can just leave this line in here. That's absolutely fine. To convert this to actual bytes, it's quite simple. For the bytes for this first one, we can just copy it from here. So this is our first line here. Clear C happens like literally everywhere. Not in this function though, apparently. Oh, come on, where can I find a clear C from? Here we go. Clear C is C3. That's the byte that makes the processor clear the C. Let's search for this MOV. We're looking just for code that will do the same thing, so we can copy the bytes. I don't feel like using an assembler for this small amount to write. We can just copy it from here, fine. So let's go here. I'll be EF13. And then this sub, A, 6, we copied that from here in the first place. This loop to load the user presets. So we can just copy that. Jump if not carry. This one's going to be slightly harder. So our jump if not carry consists of two things. Consists of 50 and this 31. The 50 will just say jump if not carry. So we'll say that. And the 31 will be the amount of bytes to jump over. So we don't know that yet, because we're going to jump over these two instructions. We haven't figured out what these instructions are. So let's find out what add is. Here's an example of an add with an immediate operand. So the immediate means this number, and the operand means something to use in the operation. So this is add A with this number. We see that it's 24 FE. Now, FE looks quite familiar, doesn't it? So FE is our other operand. 24, what do we want to add? We want to add C. Then R7, A, this is going to be a super common operation. And the code for it is just FF. And that's the end of our little condition part here. That means that these three bytes here correspond to these, and therefore for this jump we want to jump over 3 bytes. It's that easy. This is going to be a matter of copying, so we go to our save to EEPROM and we look at the very first thing it executes, which is 8F5B. That's the same thing we want to put in here. Clear A, which is also literally everywhere, as byte E4, and then return, which is also quite common, and that is byte 22. And there we go. That is some manual assembling for this 8051 assembly code. Then all you need to do is put that into the binary in some free space. Look, here's some free space. Put it somewhere in there and make some function calls. Replace the beginning of here, replace the beginning of here, and all that does is move every single save that tries to go to this location to go somewhere else, like that. Okay, that's all I've got. I hope you enjoyed that look at reverse engineering the XP-100, reverse engineering the other parts of the series. It's very similar. The 300 code is the longest. That's all, folks.